These are the circuits I have built to prove Kirchhoff's voltage law. Kirchhoff's voltage law states that every circuit must use all voltage given by the power source before reaching ground. This first circuit is very simple, consisting of a 470 ohm resistor, a 1 kilo ohm resistor, and a 2.2 kilo ohm resistor. The voltage drop across all these resistors, measuring at 1.15 volts for the 470 ohm resistor, 2.42 volts for the 1 kilo ohm resistor, and 5.31 volts for the 2.2 kilo ohm resistor. If you add up these voltage draws, you get 8.88 volts, which is very close to the output of this battery. This is why this circuit proves Kirchhoff's voltage law to be true. The reason these larger resistors have higher voltage drop across them is because it requires more voltage to push the current through higher resistance. One could determine the voltage drop across the resistor by using a DMM, like I am right now, or by using this equation on the screen right now. This is the second circuit. It has two new parts, a diode and a blue light emitting diode, otherwise known as an LED. These diodes regulate current by only allowing it to pass through one way. This diode will not let current in through this gray band. The LED also has this functionality, but it has a second purpose, which is to emit light. These two diodes are active components, meaning they only take enough voltage as they need. This diode takes around 0.6 volts out of the system, and this LED takes around 2.8 volts out of the system. This 470 ohm resistor is what is known as a passive component, meaning it acts like a sponge and takes the voltage that no other component wants. It does not have a set voltage need or want. The voltage drop of this circuit is 8.64. This is enough to say that it proves Kirchhoff's voltage law because it is close enough to the output of the battery. This is the third and final circuit. I designed and made it myself. I will be using a mechanical pencil for this demonstration because the two leads of my digital multimeter are connected to the ends of this resistor. This is so I can measure the voltage drop of this resistor throughout the presentation. This circuit has one new component, being this slide switch right here. The slide switch has one center lead and two outer leads. The center lead is always connected to one of the outer leads. The one it's connected to is determined by this switch on the top. This is a 2.2 kilo ohm resistor. It is here to protect the yellow LED from blowing out. The LED can blow out from a surplus of voltage, which the resistor here prevents from happening. This here is another diode. This time, the leads are not cut, so I can place it in a position like this, where it goes diagonal from here to here. Now, if you look at the circuit diagram, you can see that this switch will either activate the diode or allow current to flow around it. When I say activate, I mean make the diode part of the circuit, make the electrons flow through the diode into ground. Because the diode is an active component, it somewhat alleviates the voltage draw of the resistor, lowering it by the voltage need of the diode, around 0.6. So as we can see here, I switched off the diode and the voltage drop of both sides of the resistor is now 6.8. And when I activate the diode, it is now around 6.2, meaning that this diode takes up around 0.6 volts. If I place my leads on the negative and positive rails of this breadboard, you can see that no matter how much I flip the switch, the voltage drop stays relatively consistent. It stays close enough to the 9 volts inputted by the battery that it can prove Kirchhoff's voltage law. Thank you for listening.